and welcome to the Maniac talk. I'm always excited to see a large crowd in the room. We've got an exciting speaker today, so it's a nice talk ahead of us. Today, I wanted, before I invite the speaker, I wanted to start with a short story, just to warm the room a little bit, and then I'll invite the speaker to tell us his story. This story is about hyena. Some of you know hyenas. And, this hyena is on its way home, and it's a little bit late at night, and it's trying to get home as quickly as possible. At a distance, it spots a giant, big giant, blocking the path. And it's wondering, what am I going to do to close over there? So the hyena decides to shout from a distance and says, "Hey, you out there, clear the way for me." And then the giant doesn't move, doesn't do anything, just stares at this guy. The hyena shouts about 3 times, and then finally decides that I think this guy is not cooperating. So finally he says, "I know you are hearing me, but you've chosen to ignore me. I'm going back for reinforcement." So the hyena just goes away, takes a different route, takes much longer, of course, to get to the den, and shares the story with the cubs, saying, "Oh, but I got a big giant just blocking our way, so I need the reinforcement maybe tomorrow morning." So the following morning, they go back to the same place to try to see who was blocking the path for the hyena. And to their surprise, they find it was a giant tree which had blocked the path, but clearly the hyena could not see. So the moral, it was very embarrassed, of course. It had all these cage with the hyena trying to see who was blocking the path, but it couldn't see. So today, and the story behind this is that data, and that's going to be Ralph's story, data, unlike a tree log blocking the way, data has a story to tell. Unlike a dead tree log which was blocking the hyena's path, it has a story to tell. Who is better qualified than Ralph Kahn to talk about this subject? He has been with the NASA family for almost 30 years, and he's going to tell us his story, probably going way beyond that, over 100 years, I think. And it's going to be an exciting talk. So please help me welcome our speaker, Ralph Kahn.
Thank you all for coming. This is a different talk from any talk I've given before. And because of the nature of these Maniac talks, I was actually invited to give one of the very first ones, but they weren't taped at the time, and the style was very different. And so what's evolved is talking about your personal experience and how your background shaped what you do. And so I'm going to take a very liberal definition of data that includes history and how it affected me. And as I say, this challenge for me has been separating coincidence from causality. It's something that those of us who look at data and try and understand it often wonder about. I'll give a few examples of that. And as I say, at an early age, I found that data can help address the challenge of separating coincidence from causality, but only sometimes. And there's a lot of ambiguity here, and I've learned to live with that, actually. So we begin here in southern Germany. I was raised in the shadow of the Holocaust. My father's family came from a small town in South Germany called Beisingen, which is that little green dot there. In South Germany, Jews were not allowed to own farms, so they couldn't be farmers. They were also not allowed to join guilds, so they couldn't have a usual trade. So most Jews ended up either serving the Jewish community as butchers or bakers or whatever, or went into commerce. And my father's family were cattle dealers. They would buy and sell cows and move them from town to town, raise them, and so on. And my grandfather moved first from Beisingen here to Böblingen, which is a suburb of Stuttgart. And this is the synagogue. Actually, we visited it. That was my dad and my brother in 2013. That's a picture of the synagogue. This is a picture of it from way back before. And this is a different synagogue, but it looked kind of similar to that at the time. So they moved from Beisingen to Böblingen. My father was born there. And around 1928, my grandfather, he'd been elected the president of the Cattle Dealers Association. He started working in Stuttgart, in the big city. So he was no longer moving cows around. And in 1936, approximately, the Nazis, who had taken over in 1933, decided that they wanted to control the Cattle Dealers Association. So one day they showed up in his office and threw him out. And that was the end of his tenure there. But my father had been going to school at the Waldorf School in Stuttgart. Now, the Waldorf schools were founded by the Waldorf Cigar Company to train, to school the children of their workers. It was a very progressive school. It was founded in 1919. And my father got there when the family moved to Stuttgart around 1928. And the philosophy, there was Rudolf Steiner, who was an educator and philosopher, who developed a philosophy of synthesis. So, for example, they would study a stream. And they would look at a stream, and they'd read poetry about streams, and they'd draw them, and they'd learn about the ecology of the stream, and the physics of water. And it was all kind of put together in that way of thinking. And the teachers would follow the class through grades. So my father had the same teacher, Mr. Ega, Carl Ega, for about 8 years, going through grade after grade. And this was a very talented teacher who taught him this holistic view of the world. And I remember one example having to do with water. And my father would tell me, marvel at how ice floats. And he said, you know, if ice sank instead of float, the fish would all die. So this is true. Now, the causality part of that I've come to later, which is, of course, aquatic life evolved to take account of the properties of water. Nevertheless, that whole idea of looking at those things was part of what came from this Waldorf School experience. We visited there, and they have shop, they build violins, the students. They have a farm, they learn how to compost. They have a holistic education. Well, in any case, in 1935 or 36, my grandfather lost his job. They moved to Cologne, in northern Germany, and he got some kind of a job there temporarily. So this is now, they were down here in Stuttgart, and they went all the way up to there. And one day, the Waldorf School ended at that point, of course. One day, it was November the 9th, 1938, one of my father's friends came to his house and told him not to go to school. That was the day the Nazis had taken over the school. And so his parents had to decide what to do. They could no longer get out. It was now November of 1938. My father was almost 16 years old. And the British had a program called the Kindertransport, in which they allowed approximately 10,000 Jewish children of age 16 or younger to go to England if they could find a sponsor. And my father had a cousin in England who found a sponsor. And, oh, I was going to show you. This is what happened to... So that night, November the 9th to 10th of 1938, was called Kristallnacht, the night of broken glass. And the synagogues were destroyed in many parts of Germany, including Beisingen. That was a picture from around then. And when we visited there in 2013, you can see they were reconstructing it as a museum, and they're actually reconstructing a number of these as museums. There are no Jews left in Beisingen. They were all either killed or escaped. But one of the artifacts here is this, which is a barn door. They converted it into a barn after destroying it in 1938. So my father's parents had the choice of either letting my father go on the Kindertransport or to stay, and they elected to send him, which saved his life. This is not a picture of my father's particular case, but this is a Kindertransport. There were trains that took them from Germany into Belgium, and they went by ferry to England. And there's actually a book about this called Into the Arms of Strangers. So my father stayed in England for about 18 months. And then the German army marched into Belgium, and from there they were behind the Maginot Line that was protecting France from Germany, because they had a line that just went north-south on the east side of France. And so the German army was able to march in. But there was the Dunkirk evacuation that took place, and the British and French troops, many of them escaped to England before the Nazi army marched through and took over France. And my father, being in England, was an enemy alien as far as they were concerned. He was German. And so as soon as things started to get rough in England, they interned all the German Jewish kids. And they went into a concentration camp near Liverpool for a while. And the German Air Force started bombarding. The Blitz started. And in the Atlantic Ocean, the Germans had U-boats, submarines. They're called U-boats because the cross-section of the hull is U-shaped. And so they were torpedoing the British ships. And of course, Britain at the time had an empire. And the torpedoes were sometimes quite effective in destroying the British ships. So my father was there in this camp, and they asked if people wanted to volunteer to leave Britain on a ship or stay in the camp. He stayed in the camp. He looked around. The camp was a tent camp with barbed wire around it, and he figured that probably looked like an army camp to a German aircraft. He figured he wouldn't sit there and get bombed. Of course, if he went on a ship, he took the chance of being torpedoed, but he decided to take the ship. Now the ship, there we are, is called the Niro. It's actually a pretty famous story. You can Google it, and there's lots of testimony. There were 2,500 people on this troop-carrying ship. The conditions were very poor. The soldiers who kind of ran the ship, British soldiers, were at the very bottom of the army in terms of their quality, and they did a number of atrocities. They took everybody's suitcases and they pilfered what they wanted and threw the rest overboard. They didn't tell them where they were going. A torpedo hit the Niro, and it dented the stern of the ship, and it didn't go off. But gradually they made it to Melbourne in Australia, which of course was part of the British Empire at the time. They were taken off the ship, put on a train that went to another concentration camp in the interior called Hay. And then, for a technical reason, my father and 12 other of the boys, the Jewish boys, were put back on the train and taken back to Sydney Harbor. They got on the Niro again, and they continued their journey. Now, this here, it's not a great picture, but it's a panel from a quilt. This was the Kindertransport Memorial Quilt. This was my father's little panel from it. And it starts in Germany, and it goes up here. And this was the trip they took. This is Takoradi in Ghana, and then Cape Town, and then Australia, Melbourne, and Sydney. And then they went to Perth and to India. Now, in India, they let these 13 boys off, and the Jewish agency took care of them briefly. Oh, I should just point out the quote here. This quilt is in memory of the parents who saved their children by letting them go. And indeed, there was some of that. So in India, there were not very many Jews. My father landed in Bombay, and my mother was from an ancient Jewish community in Cochin, India, the Cochin Jews. Cochin Jews have a beautiful synagogue. It's still there, although the community is almost gone. Nobody knows exactly how old these copper plates are, but they gave the Jews and a certain Joseph Rabban the right to lead the community, collect the taxes, own the land, and so on. And the Hindu, the Raja of Cochin, for many generations, took care of the Jews in this area. They were merchants. Vasco da Gama stopped at this synagogue at one time, and there's a piece of a rudder from his ship there. They have these tiles. It's a beautiful place. The tiles are quite nice, and the lights, and if you're there at night. Anyway, this is a replica of the copper plates and a translation. You're not going to read it, but basically it gives those rights. And so my parents met there, and then they made it to New York. My father first, and then my mother. So this was the background. I have a couple of pictures. This is my father in 1944 in India. My mother is here. She was actually a bit of an athlete, a tennis star in India. She had all these trophies. And at the time, they don't just give trophies for showing up. You had to actually win something. So these were my mother's parents in Cochin, India. These were my parents in 2006. And this is my family. And the thought I had in putting this part together is, we are still here. And for those of you who know my work, you know, this perseverance is something I learned from these people here. This is my wife and my 2 kids. So, I was born in New York City. And I was very fortunate to get into Bronx Science. You had to take a test for that and get recommendations. And so I got there. It's a large school. There's 4,000 students at the time. From there, I went to the University of Rochester in upstate New York, majored in physics and geology. Graduated from then. You can see physics was very theoretical, kind of pure sort of stuff, and geology very practical. I was trying to bridge the gap between my parents' 2 communities, both of which had disappeared in their lifetimes. So there was a lack of reality to that. But then on the other hand, I wanted something to hold on to because current affairs had a real effect on our family. So from Rochester, I went to Harvard, got my master's and my PhD there. My thesis advisor was Richard Goody, who taught me how to write a good paper. And everybody in my group knows how well I learned that lesson. I started off assigned to a professor who was doing solid-state physics. And I started working on a project with material science of sorts. And I learned that the project was aimed at hardening electronics for missiles. That was the last day I worked on that project. We had had enough experience with war. And so I looked around for what was the most interesting thing, and at the time, the Viking missions were on their way to Mars. And so I started to study Mars. My thesis advisor, I went to Richard Goody, and he told me, well, you know, the atmosphere of Mars is pretty interesting. This is a Hubble image of Mars, but there were condensate clouds. There was a south polar cap that grows and shrinks with seasons, and a little bit of it remains in the summer. Dust storms. And so I started to study the atmosphere of Mars and use what I had learned in physics to do that. There's a dust storm from the Viking missions. I studied the energetics of these things, used the observations of the limb in order to get the vertical distribution, which is something we now do. This is the Viking Lander. And my assignment as a student was on the Viking Lander imaging team. These were the cameras. So this was a lander. It wasn't a rover like we have now. This was a meteorology boom. The high-gain antenna, the low-gain antenna is up here. These are the RTGs, the radioactive thermoelectric generators that powered the lander. This was the sampler arm that kind of had a tape measure sort of thing that went out and took samples and put them in some canisters here. These cameras were facsimile cameras because we didn't know what the conditions on the surface of Mars would be like. We figured it could be pretty dusty. So there's a slit here. The focal plane is actually at the bottom. And there was a mirror that spins. And the camera would take one azimuth in multiple channels and then step in azimuth and take the next one and would build up the picture slowly, like that. So here is the sky of Mars, and if you can see this, I don't know if you can see this, maybe if we make it a little darker up here, you can see the condensate clouds up here. This is Viking Lander 1, there's the RTG. The head of the Viking Lander imaging team was Tim Much, and Jerry Soffin was the project scientist. And I highlight these two guys because these days, there's a lot of emphasis on helping younger scientists get ahead in their careers. At the time, it was much more of a Wild West. These two guys were the ones that took a young guy like me and gave us opportunities. And so one of the opportunities I had was Tim asked me right at the beginning to design. Now remember, that in order to do this, there's 20-minute light time at the shortest between Earth and Mars. So anything that you did with the lander, you had to design in advance. It had to be checked out and then sent up to the lander, and then it would execute those commands subsequently. So he asked me to take a picture of the sunset on Mars from the Viking Lander. I was studying the sky and so on, and he gave me that honor. And so I did. And there was the picture. You can see the RTG here. Now, the thing is that I only had one gain setting. And you know that the brightness of the sky changes by orders of magnitude during sunset. But I had a facsimile camera. So what I did was I started the image out here about 15 minutes before sunset and had the camera pan slowly to here. My hope was not to saturate. It did saturate that much, but it turned out to be quite a nice picture. And it was that technique. So, okay, that was my thesis, part of it. Then I was a postdoc. And this was now in the 80s. I was a postdoc at Cornell University. My advisor was Peter Girash, and I had a lot of support from Carl Sagan, who kind of enjoyed the style of work that I did, and I'll give you one or two examples of that in a minute. I then went to Tel Aviv University, and J.H. Joseph Yoya, as we knew him, was my sponsor there. And then I was for a couple of years at Washington University in St. Louis. And one of the things I did here was I was the lead for a Mars Observer synoptic scale camera proposal. I was a postdoc trying to establish myself, and so this was an opportunity. Now, the Mars Observer program originally wasn't supposed to have a camera on it because the idea was that would be too expensive. So I said, okay, well, I can do something very cheap and just make meteorological observations. So we designed this very simple camera, proposed it. It wasn't selected, but it opened up the opportunity for other camera proposals to get in. And in the end, they selected a very expensive, capable camera that did geology and everything like that. But it was a lesson for me. I learned a lot in writing the proposal, and I was very glad to have a bunch of co-workers on that. So what I did, so let's talk about data now. And this was the kind of work I really loved to do the most. So we'll talk first about the volatile endowments for some of the inner planets, Venus, Earth, and Mars. I've got the CO2 reservoir here. In Venus, the carbon is essentially all in the atmosphere. It's about 95 bars of CO2 in the atmosphere of Venus. In Earth, we have about the same endowment of carbon, but on Earth, it's all in limestone. Limestone. There's about 1 kilometer of limestone averaged over the surface of the Earth altogether. In Mars, we weren't entirely sure. Now, the CO2 in the atmosphere, as I mentioned, it's somewhere 92, 95 bars, a lot of CO2. On Earth, it's only 0.6, about half a millibar. Now, in addition, I knew about water. There's essentially none on Venus. There's lots on the Earth. And there's some, but it's mostly ice on Mars. So the reason that there's half a millibar of CO2 in Earth's atmosphere is because in water, the carbon forms carbonate, and it combines either organically or inorganically with calcium, magnesium, forms limestone. The thing that puzzled me was this number here, because the triple point pressure of water, is 6.1 millibars. Now, the triple point pressure of water is the pressure below which you cannot have water in equilibrium. So was that a coincidence, or was there some causality? The theme comes back here, you see. So I had the idea that this might apply approximately for disequilibrium conditions. So the idea was this. You start off perhaps with a whole lot of CO2 and water stable on the surface, maybe early in the history, time and pressure of CO2. At some point, you no longer have sufficient temperature for liquid water, but you occasionally make a little bit of water in the low latitudes when it warms up in the summer, and the ice comes and evaporates. And in the process of evaporating, you make transitory liquid, and you precipitate a little bit of carbon dioxide, a little bit of carbonate. Now, that would continue until you get to the point where you can't even make water in disequilibrium, which means that not only isn't there enough water vapor to stabilize the liquid, but there isn't even enough gas up there to prevent the molecules from just freely leaving the water surface. And there was an experiment that was done by Hugh Kiefer and one of his students that kind of showed that that process could occur. Now, the exact pressure would depend on, what elevation the last bit of water was. If there was some outgassing, which is what this little dash thing means, then it would have to take it out again. You maybe make a little more transitory liquid, take out a little bit more. You have a lot of years to do this, of course, because we've got about 3 billion years in which to work with. So anyway, so that was the idea, and it led to kind of this system of carbon cycle on Mars, which bears some similarity to that on Earth, of course, the difference being that liquid water is no longer stable on the planet. And this gives us 3 planets that have some similarity. All right, one more example. This is now the Vostok ice core data in Antarctica. And this blue line here is the temperature record over 400,000 years. And you see this periodicity. Now, there's also CO2 and dust here, and there are a lot of stories associated with that. I won't have time to go into that, but I had a bit of a geology background, as I mentioned, and this periodicity here has interested people for a long time. The first order explanation of this was due to this guy, Milankovitch. The Earth's orbit oscillates. And there are three broad categories of oscillation. One of them is the eccentricity, which is the way in which the ellipsoid is shaped. Another one is the obliquity, which is the tilt of the axis. And the third one is the longitude of the perihelion, which is where in that elliptical orbit the Earth happens to be when it's closest to the sun. Mars has similar orbital oscillations. Actually, they're considerably bigger than the ones on Earth. And I note the colors here. The longest one here, I've got blue, 100,000 years. The middle one is green, 41,000 years. And the shortest one is 1923 years, and that one's red. So this is now a classic paper in Science by Hayes, Embry, and Shackleton, in which they did the following. And these colored dots represent the periodicities. So the first thing they did was they took a model, and they calculated what the solar forcing would be on Earth at 55 degrees south and 60 north. And they did the Fourier transform, and you see that most of the power in the forcing comes at 19, 23, and 41, especially 23 and 41 years, 23,000 years here, 23 and 41,000 years here, and the percent of variance. So it was pretty robust that at these shorter timescales, that is where the forcing is. However, the response, and this is now three different ice cores. This is the best one down here. And these are now three different indicators. One is temperature deduced from ice cores, which is another story. This is oxygen 18 isotopic ratio from the ice cores, and then one of the radiolarian markers in the ice cores. And you see that the forcing, especially for the most complete and best series, is all at 100,000 years. Now, this is a puzzle. How is it that the forcing is at short time scales and the response is at these longer time scales? And the explanations have been, well, you know, there was a continent, Antarctica, that moved into where there was an ocean in the pole, and maybe that would be doing it. Well, on Mars, there's layered terrain, just like the ice cores on Earth. This is a glacier in the Andes, which just shows the stratification. These are now later images than the ones we use. These are from the Mars Observer camera. But these are layers in the south polar layer terrain of Mars. There's another example of that. These are now layers that are 10 kilometers or so in thickness that can stretch for hundreds of kilometers. Beautiful layers. So what we did, and there was a student there, Jeff Plout, who was just looking for some thesis work to do, and I was thinking about this climate stuff, and a couple of geologists that were there as well, and we counted the craters in the south polar layer terrain. Nobody expected there to be any craters. It was all thought that it would be all too young, but it turned out we found 15 definite craters and 7 possible ones. Now what you do with these craters is from the moon, from observations of the moon and age dating, we have an idea of the source function, how craters accumulate as a function of time and size. And you can make a model, which is what we did, of the production age and then the deposition that could have buried the smaller craters. And you see how this tails off. That's because the smaller craters are being buried. And we ended up with an age, a production age of about 120,000 years, and steady state accumulation that was relatively small. The large crater abundance gave us the surface age, and the small crater depletion gave us the rate. So here was the conclusion of this paper, which was that the deposition rate was slower. Okay, these were 10 to 50 meter thick layers. Here's some examples of the ones we found. The main orbital climate driver for Mars from the models was the obliquity, whereas each layer took at least 10 times longer than the obliquity cycle in order to be deposited. So for Mars, again, the power in the apparent climate response was occurring at periods longer than the expected dominant forcing. And there you didn't have an ocean and a continent moving around. So now there is a possibility that the process stopped 100 million years ago, in which case this could have happened. But it's unlikely that the deposition on the South Polar Lane stopped that long ago. So is it a coincidence, or is there a common cause for this behavior? I don't have an answer to that. Well, by now it was the late 1980s. And okay, the Reagan administration was there, and they had more or less terminated the planetary program at the time. My camera hadn't been selected. I made one last-ditch attempt at trying to save my career as a planetary scientist, and I collected examples of how studying the planets taught us about the atmosphere of Earth. And this is a digital thing. And I found out that there were sort of 4 broad categories. There was discovering how planetary atmospheres are similar and how they're different, and that would expand our appreciation of how the parameter space works. And I had lots of examples of that. Then there were subtle Earth effects. So some phenomena in Earth's atmosphere are much more dominant in atmospheres, like Jupiter's magnetosphere, where the Jupiter rotation rate is 10 hours, and it's got a strong magnetic field. And so there are phenomena that show up there. Venus's greenhouse is another one. There's data available only for other planets, and my favorite example of that was the inner solar system climate record for Mars, and maybe even the Moon, which we still have as yet to tap. And I'm hoping someday we do that. And then just the new ideas. So anyway, again, thinking broadly, this is that the Waldorf School kind of way of thinking about these examples. That was what I came up with, but it didn't work, and I had to change fields. So there was Earth. I spent 1 year at NASA headquarters. Shelby Tilford and Dixon Butler were my mentors there, and I was the deputy program scientist for EOS under Dixon Butler. And my job was to work toward what we now call the data system for the Earth Observing System. I had been working with many different kinds of data, and you can see, chemistry and geology and atmospheric measurements. And so I had the right attitude, in their opinion, to start thinking about, at the time, I remember I did an inventory. There were about 14 or 18 end-to-end data systems. Each instrument had its own data system from beginning to end. All the data was in different formats. There was no documentation that anybody but the team could use. And the objective was to move in that direction. The community was fairly responsive to that. Dixon and Shelby were very good leaders, and that happened. I spent a year at headquarters, and at that point, it was kind of diminishing returns for me. So I spent another year at Goddard. Al Arking hosted me here as a visitor. And after that year, I was running out of a career. And I was within a month or so of not having a job. Now, at that point, my old thesis advisor, Richard Goody, one of his pals was a fellow named Mustafa Shaheen, who was the chief scientist at JPL. And it turned out that Moose was on his way to Russia to give a talk on planetary atmospheres. And so Richard said to him, well, why don't you stop at Goddard, and my old student, he might have something you can use. So I gave him the paper on the evolution of Mars's atmosphere. And I forgot about it, and the weeks were ticking by, and I was getting to the end of my job. And Moose calls me up about 2 weeks after I'd gone to Russia and come back, and he asked me to come and interview at JPL. Now, he was on the top floor of Building 180, and he sat me down. There's Moose. He sat me down, and he queried me in detail about every one of my papers up to that point. He had actually read every one of my papers. And when we were all done, he offered me a job on the spot. And I said, phew, thank you. And I wasn't quite sure how to call him. And I said, well, how should I call you? The chief scientist at JPL. You just rescued me from oblivion. And he said, think of me as a brother. This was Moose. He was wonderful that way. And so forever after, he was Brother Moose to me, and I have emails from him, Brother Moose, and so on. My other supporter at JPL was Rich Zurich, and he was a Mars scientist, is a Mars scientist. And he helped me in many ways while I was at JPL, so I wanted to just mention him. Now, one of the things, okay, the planetary program was winding down. My Mars camera had not been selected, which meant I wasn't going to get a university job as a planetary scientist. And even to ask the kinds of questions about causality that I like to ask, even to ask those questions, you have to have data. Well, as it turned out, although the Reagan administration had cut back on the planetary program, they had initiated the Earth observing system. And so there was this spacecraft, the Terra spacecraft. There's MODIS, the big Goddard instrument here. And MISR was a JPL instrument. And they needed an aerosol scientist. And so I became the aerosol scientist for MISR. And I had to start learning about the Earth. There was an enormous transition for me because for every paper on a subject for Mars, there were hundreds of papers on that subject for Earth. So you couldn't write a paper about the evolution of the atmosphere of Earth. Maybe you could write a book about it, but it would be a review book of lots of other things. For Mars, you could actually write a paper about the... So that was an adjustment for me. The other thing was that when I studied Mars, I mean, people cared that I got an answer, and they listened politely when I explained about the evolution of the atmosphere or whatever. They didn't really care what the answer was, but they were intrigued that you get an answer. Now, for Earth, it's the other way around. There were a lot of people who don't want us to get answers. And when we do, they care a great deal about what those answers are. And that problem has gotten progressively worse for those of us that do this kind of work. Anyway, at this point, I had to develop an appreciation for aerosols in Earth's atmosphere. Now, on Mars, water is a rock, it's ice. And so aerosols are the whole story. On Earth, not so much. So I'm going to go quickly through a couple of pictures. This is a dust storm. I was showing this is a dust storm from space, CWIF's image. There's a dust storm in Phoenix. This is some wildfires in Alaska, and you can see the smoke here. And then this was when the region around JPL was burning a couple of years ago. This was a station fire. Volcano, this was Mount Etna. MISR, MODIS. This is from the space station. Gives you a little bit more. These are aerosols. They're in the atmosphere. Why do they matter? Just very quickly here. One of the things that particles do in the atmosphere over dark ocean, they reflect sunlight, so they can cool the Earth that way. Another thing they can do is if they're dark particles, if they're soot or smoke, brown carbon, black carbon, desert dust, they can absorb, warm the atmosphere to some extent. And then in order to make a cloud, you have to collect water molecules, vapor. And in most situations, that requires an aerosol, a particle, to collect the water. And so aerosols mediate the formation and the properties of clouds. And in the last 10 or 15 years, we've learned a lot more about this. But these are sort of the key things that aerosols do in the atmosphere that seem to matter. Now, why does that matter? I'm going to highlight my colleague, Steve Schwartz, who's forced me into the big picture on this to a large extent. This equation here, the simplest conceivable way of relating the climate response, the change in maybe surface temperature, to the forcing, which includes the greenhouse gases and includes all the things that the particles do, is just the forcing times some quantity, linear. Now, it's not linear. We know that. But as a first diagnostic, just like taking the mean global surface temperature as a diagnostic, this is the way models tend to be assessed. And the way this is done is we have a temperature record that goes back over 100 years. And we have our ideas about what the forcing is due to greenhouse gas increases, changes over time. And so if you run the models back 100 years, you can see what the climate sensitivity is, what this parameter is, and then presumably that should be able to give you confidence that you can extrapolate into the future. Well, it turned out that that didn't quite work initially. When they put in the greenhouse gases, they expected an increase in forcing that would have amounted to 2.1 degrees Kelvin over a 100-year period that ended in 2000 approximately, and the observed was about 0.8. So the first IPCC report in 1990 had this kind of issue. By the second one in 1995, they realized that by including aerosols, they could get this into rough agreement. But there are a lot of uncertainties, and the models are all over the place in a lot of respects. And what matters is not just the mean global surface temperature, but the regional temperatures. So that's why it matters. So there's MISER. This is the instrument that I've been the aerosol scientist for. It has 9 cameras pointed in 9 directions. And so before launch, well, okay, let me give you an example quickly of how this works. So these are now 3 views that I've processed roughly the same way. This is the nadir view looking straight down. This is one at 60 degrees forward and 60 degrees aft. This was a fire in Los Alamos. Los Alamos is there. And the first thing you see is that the background here is brown, and here it's a lot lighter. That's because you're looking through a steep atmosphere. You're looking through twice as much atmosphere in these 60 degrees as you are looking straight down. And so here you see more of the surface. Here you see more of the atmosphere. By looking at different angles, you get some information about how much aerosol is in the atmosphere, aerosol amount. Then if you look closely, you'll see that the plume looks a lot more pronounced here. And that's, again, because of the, but you see, they look a little differently in the forward and back scattering directions, and they're kind of bluish. Well, those turn out to be diagnostic for particle properties, for the size and shape and brightness of the particles. These are small particles of smoke. And then the last thing I want to show, if it shows up here, is you see this cloud. This is a cloud that's quite high up. And this doesn't appear to move relative to the background because this is near the surface. But this cloud moves out all the way out over here as you look from the different angles. This is parallax, which allows you to get the height. If you have a plume, you can get the height. So here's the scattering angle, the geometry, and I did some pre-launch studies to show the relationship of particle size to the scattering at different angles, and the shape, and the shape came a little later, and the light absorption. And so these are the phase functions as a function of this angle. And of course, we sampled different angles in here. Well, it's a highly underdetermined problem. So what we had to do, so I took all the existing aerosol transport models and aggregated them and looked at what the mixtures of different aerosol types were around the globe. And it turned out that there were 5 groupings doing a cluster analysis of all this data, different layers of different aerosol types, sulfates and desert dust and smoke and so on. And so this was dust, and this was smoke, and this was dust and more dust. This was pollution particles and smoke mixed. 5 groupings and about a dozen different types, which is to say different rough proportions. And it was pretty consistent. It was remarkably consistent. And so then we did a study, and I had this really great programmer. He just liked to do graphics programming. And he was one of these guys that worked all night and drank the Yoo-hoo chocolate drink and ringdings. And he was from India. Pranab Banerjee was his name. And he wasn't that interested in the science, but he was fascinated with doing graphics. And so I had this idea of making a tetrahedron with 4 aerosol components as a sort of mixing diagram. So the tetrahedron, the vertices were 100% of each of the 4 components. The edges were binary mixing. The planes were ternary mixing, and the voxels inside were all 4 components. And so we created this structure, and these are now slices through it. They're of different sizes because they're different slices through the pyramid. And So we had 4 components and 4 tests. These were chi-squared tests between an assumed behavior and a retrieved behavior. And so we colored 4 sub-boxes with the sensitivity for each of those 4 tests, and then colored the background with the most sensitive one of those. And it gives us regions in this space that tell us where we have a retrieval that matches the observation. So you assume certain things, you run a forward routine, you simulate what the atmosphere should look like, and then you try and retrieve on that with different sizes and different shapes and different single scattering albedos. And how far away from the right answer can you get and still get successful chi-squareds? And that tells you your sensitivity. And so we did that, and the result was we were able to come up with a climatology, relatively simple one. These dashed lines are, and this is the phase space again, these are the phase functions, and those are the different angles that we sample in mid-latitudes as just an example. So there we were. Then we generated a retrieval algorithm on the basis of this. My colleagues, Dave Diner, who was the Miser PI, and John Martinchek, we kind of did this algorithm. I subsequently built a research algorithm, which was in some ways different, in some ways similar to the standard algorithm. The standard algorithm was designed to run quickly on all the data, a lot of data, because it comes down constantly. And we were able, with that algorithm, to get aerosol optical depth, the amount of aerosol, and this is just 10 out of our 16 years, almost 16 years of data, different seasons, different years, and I just blew these ones up so that you could see this is real data, and it includes the bright deserts because the multi-angle observations allowed us to do that. Plume height, that was another thing I mentioned. This is now a little dust storm in the Videla Depression. This is the nice MODIS context image. This is a Miser detail. This is the stereo height, and it's right near the surface, so it comes out blue. This is the optical depth, so we do see the dust, and this is now, again, the context image from MODIS. This is now transported dust off the coast of Mauritania, Miser detailed image. And this is now up above the surface. We get this is the stereo height here. This is now the atmospheric stability structure. And we found, this didn't come as a surprise to LIDAR guys, but to us it did, because we hadn't read their literature well enough. But we've got it all together now. Aerosols, if they're not in the boundary layer, they like to accumulate in layers of relative stability in the atmosphere. So that's what happened here. David Nelson was my colleague for many years. He retired in the last fall. He built the algorithm that does the very best job in getting the plume heights. Okay, so now what are we doing with some of this data? I'll give an example here of the injection heights. Maria Val-Martin worked with me when she was a postdoc and continues to work with me. And we use the stereo heights, and she did a nice climatology of the heights, and we found that somewhere around 18-20% of smoke plumes actually inject smoke above the boundary layer. This was a surprise. The models, the climate models, had mostly injected it all in the boundary layer rather than above. Smoke that's above the boundary layer will travel farther. It'll last longer in the atmosphere, have a bigger climate impact. Marina Petrenko has worked with me first as a graduate student, then as a postdoc. Now, the two parameters that a climate model will use to represent aerosol sources are the injection height and the source strength. So I had the idea that if we have a snapshot of optical depth from a satellite, we take the model and run it in the forward direction with different source strengths and look for the match. And Maria took that and ran with it, did a whole PhD thesis on it, and is now working on an even more elaborate and more accurate way of doing this whole thing. And it turned out that there was some systematic behavior. I don't have time to go into the details, but there's a nice paper on all of this stuff. Anyway, that's one thing we did. Now, the third thing, okay, we had the optical depth and the plume height. Third thing was aerosol type. And this is now smoke from Mexico off the coast of the Yucatan here. And this is now the optical depth, the angstrom exponent, which is the spectral dependence of optical depth, which is related to the size in some ways that's sometimes clearer than others. And then the fraction spherical, which again we get from those phase functions. And you see that these are small spherical particles using the same color charts and the same quantities. Dust blowing off the Sahara, again, the optical depth. Now the angstrom exponent, these are big particles and they're non-spherical. So there's information there. And if you put this all together, you can map it out globally. There are a lot of stories here about what we can and can't do. There are severe limitations, but there's information here that's unavailable on a global scale elsewhere. My colleague Barbara Gately also retired last fall at JPL, worked with me for many years trying to validate these things. We validated the optical depth very well because of AeroNet. AeroNet is a system of sun photometers on the surface of Earth that make very high-quality direct sun measurements of the optical depth. But their ability to constrain aerosol type is a retrieval with a lot more assumptions in it. So Barbara and I tried to validate it, and we did it by comparing with expectation, because you know that dust comes off of North Africa, so you look at some places where you're sure there's dust and see whether that's what you're getting, and so on. We struggled with this. And we learned some things, and there's a paper we had last year in that before she retired. But the best way of getting this kind of information was from field campaigns. And I participated in more than a dozen field campaigns. But the one I wanted to highlight here was the Salmon Campaign in Morocco. Now, this was a campaign that was organized by German universities. And they invited me to participate. I was the only American. In fact, they had one Moroccan student in this first Salmon Campaign and me. And we were in this place called Ouarzazate. The high Atlas Mountains are here. It was a pretty desolate place, as you can see. And I got there, and in one of our first meetings, we're sitting around the table, and there were about 25 German scientists from different institutions. And one of them goes, Kahn, K-A-H-N, that's a German Jewish name, isn't it? Yes. Well, then they all got very quiet. So I thought, oh my goodness, here I am in the desert. So I told them the story. I told them the story of the Waldorf School. Now, my father's teacher, Carl Ega, turned out he ended up in upstate New York when I was a very young child. My parents visited him, and he and his wife visited us. And on the last time that he was there, I must have been 6 years old, I remember my father and Carl Ega sitting on opposite sides of the dining room table, talking in German. And all of a sudden, my father teared up. Now, my father's German. He never tears up. And the German, I didn't understand the German. My German was never good enough to understand it. But I learned later what happened. My father asked Ega what he had done during the war. And after November 10th of 1938, the Nazis took over the Waldorf School, and they were all kicked out as well. And he was an anti-Nazi. And what they did with anti-Nazis is they put them in slave labor. And so Ega was telling him about this. And he said, well, they put me in a torpedo factory. And every once in a while, I would put sand in the mechanisms to play a trick on the Nazis. You remember the Niro? There was a torpedo that hit that ship. I should have told you that. If I forgot to mention that, I should have. A torpedo hit the Niro. and it dented the stern of the ship, and it didn't go off. And that's how my father made it to Australia, and so on. And when he heard that story, that's when he teared up. So after that, I got along very well with everybody. That's Andreas Petzold sitting in his Falcon F-20. This was the Paternavia. We had 2 aircraft out there. This is the HSRL. We had actually we had a good old time. We went and looked at Orzazat. We had one of the best validation days of all time. You see here Miser retrievals, and we have this little dust storm here, which we pick up very nicely. But then if you look here, this thing I've circled in white, in the single scattering albedo, these are kind of brightish particles. The angstrom experiment, they're small particles, and they're very more spherical than everything around. Small, spherical, bright particles. Well, it turned out, you see this dashed red line, just by chance, the Falcon F-20 with HSRL, with the high spectral resolution LiDAR, went right through that thing. And it turned out, and I found out this after I had shown them the Miser data, they had 2 little layers of pollution that had come from the coast of Algeria. We were able to identify that as distinct from the background dust. And you can see these are the back trajectories, and this is where it came from. And if you go just outside that box, which is where point 1 is, this stuff coming from the Atlantic didn't have that. So there we go. So now we have the research algorithm, and my colleague Jim Limbacher and I, and now our new hire, Preeti Manoharan, are working at improving the research algorithm. We get more information out of the algorithm, and we're getting late, so I'm not going to go into a lot of details about this, but it's still aerosol type. It's still a qualitative thing. And we have to make assumptions because it's an underdetermined problem about the particle properties. So again, this Waldorf School view of how things fit together, there are communities that make aircraft measurements, surface measurements, that build models. I mentioned a little bit about the models when I was talking about how we came up with the climatology to go into the algorithm, the in situ measurements that give us detail that's unobtainable from space, and the satellite that gives us frequent global snapshots of everything. Well, one thing we're lacking is systematic measurements of the microphysical properties of particles. And this is one of the sort of future things we're hoping to do called SAMCAM, Systematic Aircraft Measurements to Characterize Aerosol Air Masses. Working in the field for about a dozen field campaigns, I've developed a very healthy respect for what the guys who do these aircraft measurements can do. And so we've come up with a concept, at this point it's just a concept that we're working on, to make the microphysical measurements that will allow us to make better assumptions about the particle properties in our retrieval algorithms. And then in addition, in order to translate between the optical properties that we retrieve from space and the aerosol mass that's book-kept in the models, you need something called the mass extinction efficiency, relating optical properties to mass for particles. And we're planning to measure that too if we get the chance. So finally, this is my group now. Very proud of my group. We study aerosol amount, aerosol type, and the layer heights. Our 2 broad areas of study are air quality and climate. And I have highlighted in red various folks from my group that do this work. There's the research algorithm. There's SAMCAM, what I just mentioned, the IPCC report, which we feed in various ways. These are my colleagues. I've mentioned most of them. I guess I haven't mentioned Marielle, who's working on air quality. She's a graduate student at Georgia Tech, working with me on some air quality stuff. And Lauren Zamora, who is studying aerosol cloud interactions in the Arctic. Maria doing the source strength, and the other Maria doing the injection height, and Jim working on the research algorithm. And I'll stop there. Thank you.
In the interest of time, I think, one comment, quick question, then we'll wind up.
Oh, your father's teaching teacher was doing interdisciplinary science before anybody talked about it.
Well, he talked about it. He
No.
talked about it. That was his thing.
Yeah, that's the point.
Absolutely.
Way ahead of.
Yep. Yep. So yeah, the torpedo factory. And, yeah.
Okay, let's stand clap one more time. Thank you.